In this video, we're going to talk about line integrals with respect to coordinates. So first, let's just talk about this title. When we do an integral along a curve in either 2D or 3D, we call that a line integral. And to say that the line integrals with respect to coordinates means that the differentials that we see in here are something like dx, dy, or possibly dz. So this is in contrast to some line integrals that we talked about earlier. If you had a line integral like integral along c of some function times ds, that's called a line integral with respect to arc length because we see that differential ds on there. So that's just an overview of the topic we're going to be looking at. And in this context, we would be given a function that we're trying to integrate along our curve, and we would also be given a description of our curve. So first thing I think we should do is draw a picture of this curve C and just make sense of that geometrically. So let's draw in the xy plane, maybe go up in increments of 5 just to make sure we can get all our points on here. So that's 25 that way and 25 in the y direction. And let's see if we can plot this. So the curve is really divided into two parts. On the first part, we're traveling along the parabola y equal x squared, and we're doing that from the point 39 to the point 525. Okay, so going up in increments of 5 here, let's just label stuff. So 3, 9 might be roughly about there, going up to 525 along the curve y equal x squared, and then from there, we're going to travel horizontally. So we're going from 525 over to 1225. So let's say about there. So when this curve is divided into two different sections, it's usually best to label those two curves. So we'll think of this as being C1 and then C2, and the curve C is really C1 and C2 sewn together. So now that we've got a visual, we're going to try to parameterize our curves. So we're going to deal with C1 and C2 separately. Let's start with C1. So for C1, let's highlight the information that we've got in the question. We know that we're traveling along a function that has the form y equal f of x. And when that happens, the easiest way to parameterize your curve is to let x equal t and to let y equal f of t. So meaning just take whatever function you're working with, in this case it's x squared, and just replace the x with a t. So you could say x equal t and y equal t squared then captures points that lie along that parabola because our points have this relationship that y is equal to x squared. And then we always need to indicate the value of our parameter as well. So if we look at our points here, the x values are going from 3 to 5, and that means that since t is equal to x, that means t is going from 3 to 5. So that gives a description of C1 just in terms of a single parameter. So the x and y values are changing as we go along that curve, but we've now completely described those points just in terms of t. So we want to do the same thing here for C2. Okay, now C2 is going to work a little differently. It's a straight line segment. So when you have a straight line segment, you can think about what's going on with your x and y coordinate. Let's look at the x coordinate first. So the x values are starting at 5, and over the course of that line segment, the x values are increasing by 7. You can just think 12 minus 5 is our net change. So 7 units of change in the x direction. So we're going to write 5 plus 7t. So you're taking the amount of change, multiplying that by t, and then we're going to let our parameter range between values 0 and 1. When t is equal to 0, you get your starting point, and when t is equal to 1, you get your end point. So if we did the same thing for the y coordinates, now the y coordinates are starting at 25, and there's no change in the y values as we go along this line segment. So you just say y equals 25. You could think of that as 25 plus 0t if you follow the pattern, but more simply, you're just saying, well, y is constant, so we'll just say y is equal to 25. So that's great. That's parameterization of both of those curves there. Now, when we get into the calculation, we're going to also need to know dx and dy. So I would suggest that we do that part of the calculation just under our boxes here so that we've got everything collected in one place. So let's look back at C1 here and let's calculate our dx and our dy. So just taking differentials in the usual way, we take our derivative of x, which is 1, and then just multiply that by dt. So in other words, dx is just equal to dt, and dy is equal to 2t dt. Let's do the same thing for C2. So dx is going to be 7 dt, and dy is going to be 0 because y was a constant. So ideally, you would have all this stuff in one big box so that we understand that these differentials here refer to C1, and then we could have all this stuff here in a second box so that we know those differentials over here belong to C2. So we'll need that when we set up our integral. Okay, and then let's flash back to the question and just remember what we're trying to evaluate. We'll write that down again. We are trying to evaluate the line integral. So integral along C of y dx plus x dy. So I write that down just so we don't have to keep scrolling back. Right, so what we'll do is we'll calculate the line integrals along C1 and C2 separately. So let's first do the line integral along C1 and what we're integrating y dx plus x dy. So we'll figure out this number, then we'll do the same thing for C2, and we'll just add the results together at the end of the problem. So if you have a curve that's sewn together out of two different curves, just calculate the line integrals separately and then add up the results to get the line integral over the whole curve. We'll talk about the details there a bit more at the end. All right, so integrating over C1. So that means we're looking at stuff inside this C1 box here, and let's just sub in for y dx plus x dy. So y is t squared, dx is dt, x is t, and dy is 2t dt. So if we just literally sub in, that's what we get. And then grab the values of your parameter from that box as well. T is going from 3 to 5. Okay, so let's clean up our integrand. We are integrating from 3 to 5. Integrand here, t squared dt plus another, this would be 2t squared dt. So if we just add that together, that's 3t squared dt. That looks pretty fun to integrate. That's going to give us t cubed, and we'll evaluate that at 5 and then at 3. So 98 is the value of that first line integral. So let's do the same thing for C2. Do line integral over C2. Integrand is still y dx plus x dy. And we'll just do a little bit of scrolling here. Look back now at our box for C2. So let's look at all the information in this box here. T will be ranging from 0 to 1. dy will be 0. So one of our terms is going to disappear. Dx is going to be 7 dt, and y is going to be 25. Okay, so that takes care of all the information we need, and let's try plugging in here. So we said our t values would range from 0 to 1. We said that dy was going to be 0, so that second term is just going to disappear when we sub in. Y dx, well, y is going to be 25, and dx we said was going to be 7 dt. Okay, so our integral looks like the integral from 0 to 1 of 175 dt. So integrating that, we get 175t evaluated at 1 and then at 0, so that's going to give us 175. So now that we've evaluated our two line integrals, we can say, well, the line integral over the curve C of our integrand is the same thing as the line integral over C1 plus the line integral over C2 of that same integrand. So you'll be able to say that every time your curve C is just sewn together out of two different parts, then you can break that up into two integrals. So here we have our answer coming up. We said our first line integral had a value of 98, second one was 175, so final answer 273. So I think probably the trickiest part of this problem is the parameterization. Anytime you're faced with a line integral problem, whether it is with respect to the coordinates or whether it's with respect to arc length, there's a possibility that you may need to parameterize your curves. So we got a little bit more practice here with the idea of parameterizing a function like y equal f of x, and we also got practice with parameterizing a straight line segment. So those are two of the key tools that you'll need when dealing with line integrals. Thanks for watching.